Hi, I'm Tom, and today I will be presenting hbACSS, how to robustly share many secrets. First things first, for this talk to make any sense, we need to briefly describe secret sharing. In a threshold secret sharing scheme, a dealer has some secret S that they wish to share with a committee of n different nodes. Each of these nodes receives a share of the secret, such that t+1 shares can be combined to generate the original secret, but any less than t+1 shares will reveal nothing about it. In Shamir's secret sharing scheme, shares are points on a polynomial, and interpolating the polynomial to find the y-intercept reveals the secret. Verifiable secret sharing essentially adds a layer of protection over secret sharing to ensure that it still functions correctly in the presence of malicious players. So, why do we care about verifiable secret sharing? Verifiable secret sharing, or VSS, is used as a subprotocol in many different sorts of distributed applications. It can be used for anonymous bulletin boards, in which the message being shared is the secret, and some MPC program mixes messages together to disassociate them from metadata. It can be used to instantiate randomness beacons, which provide on-demand cryptographic random numbers for distributed applications. It can be used for distributed key generation to allow the creation of a threshold signing key without the need for a trusted third party. And more generally, it can be used for general multi-party computation, allowing distributed users to calculate useful functions on their private inputs without revealing them to anyone else. So, because verifiable secret sharing is often used as a subprotocol in distributed applications, these applications inherit the properties of VSS, and unfortunately, VSS is often a bottleneck. So if I'm a performance-oriented application developer, I would prefer to use a fairly efficient VSS. Unfortunately, if I want good performance, then I'm often going to be making assumptions about network synchrony, or maybe I might loosen my fault tolerance a bit, or perhaps I might not try to scale my application to very many parties. Therefore, if we want to see more scalable and robust applications, then we should develop an efficient VSS that can function well in those settings. In particular, we would like our protocol to be asynchronous, meaning that it should work without making any sorts of timing assumption. This inherently captures resilience to network partitions or just general congestion. We would like our protocol to be optimally Byzantine fault tolerant, which in the asynchronous setting means that up to a third of the participants can behave arbitrarily, they can go offline, or even maliciously craft fake messages. We would like our protocol to be complete, meaning that rather than the secret merely being reconstructible at the end, we want all honest parties to receive a valid share. We found that many previous works that defined AVSS added some extra property for their application to capture this notion that we do want guaranteed delivery of every share, because it's important for many different applications, particularly MPC. Lastly, we would ideally like to have no trusted setup, meaning that no structured reference string needs to be generated to use the protocol. This is mainly so that it can be deployed in different applications without having to add logistical overhead. We prefix all of our protocols with an HB, which is short for honey badger, a creature that is well known for its high degree of fault tolerance in adversarial settings. We use ACSS to refer to asynchronous complete secret sharing, which is essentially VSS that incorporates our notion of completeness from the previous slide. To construct ours, we use three fundamental primitives. The first is polynomial commitments, which we use as a cryptographic abstraction that allows a prover to commit to a polynomial and then prove evaluations on that polynomial relative to the commitment. We need an asynchronous reliable broadcast to allow the dealer to broadcast some polynomial commitment, C, and recipients to verify that they all receive the same commitment. And lastly, we need to provide a provable communication channel by which a dealer can verifiably send a share and an evaluation proof relative to this commitment to each recipient. Finally, for the last step, we use a BRCA-like agreement, and each party will output once they've seen n-t parties indicate that they believe the secret is reconstructible. In an asynchronous setting, you can only ever wait for n-t parties because the other parties may have crashed, and if you're waiting for them, you'll be waiting forever. Unfortunately, this means it's impossible to distinguish between an adversarial node and one that is simply slow. And it's possible that an honest but slow node may not have received a correct share, but is unable to let anyone know in time. Therefore, if we want to have some sort of completeness mechanism, we need some way for this extra party to receive their share, even if they're slow. Previous works handled completeness by sending redundant information to allow for share reconstruction, such as using a bivariate polynomial to share a secret. However, this adds overhead to the whole overall protocol and results in a suboptimal best-case performance. Instead, we create a dispute mechanism to achieve completeness that won't be triggered unless the dealer acts maliciously. To implement our dispute mechanism, we make use of asynchronous verifiable information dispersal, or AVID, which essentially allows a sender to take a message, break it into chunks, and disperse it amongst the set of nodes. Then, any interested players can receive those chunks and reconstruct the original message. In this case, a message would consist of a share and an evaluation proof, so each message would only need to be retrieved by one node. As AVID, by default, is not private, each message would need to be encrypted with help from a PKI. Parties can implicate a faulty dealer by allowing other nodes to grab their encrypted message and show how the message decrypts, and then any interested parties can check the proofs and see if the dealer was malicious or not. If so, we enter a share recovery phase. Once we've entered share recovery, we know that the dealer is malicious, and we are no longer concerned with the privacy of their secrets. And instead, we try to recover the whole polynomial that encodes them by any means necessary. The simplest way to do this would be for all parties who have valid shares to send their shares to anyone who needs them. We use this in the first version of our protocol, hbACSS 0. If we wanted to be more bandwidth efficient, we could use a batch reconstruction technique to open many different secrets at once in an asymptotically more optimal way, which we use for the other two versions of our protocol. But of course, to open many secrets at once, you need to deal many secrets at once. And our schemes benefit substantially from batch amortization, and we generally consider the batch setting, where a dealer is dealing many secrets at once, to be the primary use case for our ACSS protocols. In particular, in a batch amortized setting, reliable broadcast and AVID become asymptotically optimal, efficient share recovery becomes possible, and polynomial commitments become less computationally intensive, as we're able to reuse some parts of the computation in multiple different proofs. Moreover, we note that batching is suitable for many different applications, in particular general multiparity computation. Now, the last major implementation detail that is yet to be described is the polynomial commitment. Recall from earlier that polynomial commitments allow a prover to commit to a polynomial and then verify evaluations relative to that commitment. As you may imagine, there are many different ways to commit to a polynomial and prove evaluations on it. The first of these comes from a paper that we refer to as KZG, and is the first row of this table. It is the original polynomial commitment and is still very popular today due to the fact that it is ideal in size and verification cost, but its O of n proving time hinders its use for VSS. However, if you're okay with that, and you're okay with the trusted setup required in order to use it, then if you combine it with hbACSS 1, you create the first asymptotically optimal bandwidth batched ACSS protocol. Another important polynomial commitment scheme to consider is AMTs, or Authenticated Multi-Point Evaluation Trees. This work seeks to improve on KZG polynomial commitments by improving the prover performance to log of n, but at the cost of a log of n size and verification. Both of these protocols have homomorphic commitments and evaluation proofs, a property that we leverage in the first version of ACSS that uses a bandwidth-efficient share recovery, hbACSS 1. Lastly, we also contribute our own polynomial commitment scheme, which we refer to as hbPolyCommit. The goal of this scheme is to offer a performance that is comparable to AMT's, but without the need for trusted setup. As our solution involves non-homomorphic share evaluation proofs, we contribute a third ACSS protocol, hbACSS2, that can handle such schemes. In constructing hbPolyCommit, we first note that a polynomial evaluation is just the dot product of two vectors, a vector of coefficients that make up the polynomial, and a vector of powers of the index that the polynomial will be evaluated at. We can therefore take an inner product argument or dot product argument from the bold proofs paper and repurpose it as a proof of polynomial evaluation after modifying it to make it zero knowledge. This inner product argument is an interactive proof protocol that can be made non-interactive through the use of fiat Shamir. When using fiat Shamir, it is important that the challenges the verifier generates are the result of hashing the entire proof transcript up until that point. We note, however, that a prover who is proving multiple things to multiple different verifiers at the same time can have each of these proof transcripts function as a leaf in a Merkle tree, the root hash of which can be used as a challenge. Applying this allows us to save a lot of computation for each proof and reduces the overall amortized number of group operations from O of n to log n. We note, however, that there are some field arithmetic operations that are still O of n, but they are non-dominating at the player ranges that we consider in this paper. Lastly, we implement all of our protocols and evaluate them on a single machine. Any communication between players is implemented as different threads running on the machine and sending serialized messages back and forth. We first measure the performance of hbPolyCommit against AMTs, with the prover computation costs at the top and verifier computation at the bottom. As you can see, both of these scale approximately the same way, but have different jaggedness to them due to finer implementation details about how both of these algorithms work. Next, we go ahead and implement all of our ACSS schemes with different polynomial commitment backends. At the top here, we have the error-free case in which an honest dealer deals a share to honest parties. As you can see in every case here, the scaling is linear, with the purple at the top being hbACSS2, which requires an approximately 3x overhead relative to the other versions for reasons that are explained in the paper. At the bottom here, we have what we can refer to as the maximally terrible case, in which a corrupted dealer sends t different invalid proofs, all of which will result in an honest party needing to recover their share. The protocol does still miraculously output, everyone just wasted a lot of their time in the process. In this, we have a clear divergence of behavior. In hbACSS0, the one with our simple share recovery, we see a clear quadratic trend that contrasts sharply with the linear trend of the two protocols at the bottom here. At the very bottom, we have hbACSS1 with AMTs, but with the caveat that they don't have interpolation of polynomial evaluation proofs. Essentially, when we implemented their scheme in our framework, we found that interpolating these proofs, each of which is logarithmic size, actually imposed a lot of computation and caused it to behave similarly to hbACSS0 in this case. So due to that, we include an extra benchmark that does not include this necessary part, just to show that the behavior would be linear, except for this one computational bottleneck that isn't AMT's fault, as they were never designed to actually do this. Anyway, our key takeaways from all this are that hbPolyCommit performs similarly to prior state-of-the-art, but without the need for trusted setup, and that our different hbACSS versions perform differently in different scenarios. And we have a full discussion in the paper for when one might consider using each of these. In conclusion, in this paper we have created the first ACSS protocol with simultaneously optimal bandwidth and optimal fault tolerance in the batch setting. We created a polynomial commitment scheme which performs similarly to prior work without requiring trusted setup. If we are okay with an additional log n bandwidth factor, then we create the first ACSS protocol practical enough to implement. But at the end of the day, all that we're aiming for here is to help kickstart development in the space in order to encourage more robust applications to be developed in the future. Thank you.